Hello and welcome to my talk. I am Markus Sommer from the Philipps University of Marburg Distributed Systems Research Group, and I will be telling you a bit about our project ProgDTN, Programmable Disruption-tolerant Networking. We start off with a little primer on DTN. It was originally invented by NASA for use with their deep space probe network, but in more recent years it has also found quite a few interesting use cases back here on Earth. As the name implies, it is highly resilient against both link disruptions and high link delays, usually measured in terms of minutes, if not hours or even days. And it operates in a store, carry, and forward architecture. That is to say that messages are not directly transmitted from source to destination, but rather they may be stored on intermittent nodes for even long times while they wait for links to become available. Now, what are interesting use cases for DTN? It is basically any such use case where there is no established communications infrastructure. This might either be because infrastructure has never been there in the first place, such as for example in more rural areas, or the infrastructure may have existed at a previous point but has since been destroyed, degraded, overloaded, or any combination of these factors. What is the problem that we are trying to solve with DTN? Well, when you have a piece of delay-tolerant networking software, it usually comes with a predefined set of routing algorithms. Sometimes that set is one. In this case, you only get one single algorithm, or maybe you will get two or three if you are lucky. And as the operator, you have to choose exactly one of these predetermined algorithms. Also, these algorithms generally only use the local network topology to make their routing decisions. If even that, sometimes algorithms such as epidemic routing don't use any information at all. They just send everything to everyone and hope for the best. But now what do you do if you have a use case, if you have a scenario for which none of these provided algorithms is particularly well suited? Well, you can either deal with it, choose the one which you think is least bad and hope that it works well enough, or you can attempt to modify the networking software. In case where it is proprietary software, that might just be straight up impossible. Or if it is open source software, it might be technically possible to modify, but practically infeasible in the sense that it would take an unfeasible amount of time and effort to get to know the software to a point where you can make meaningful modifications to it. Of course, this is not a new problem. We had the same problem with traditional networking, where you were generally limited in your capabilities by the capability set provided to you by your hardware vendor. This was eventually solved by programmable networks and then also software-defined networks, where you have a vendor-agnostic configuration language in which you can define forwarding rules and then push those rules onto compatible hardware. This concept has not previously been applied to DTNs because they lack the central coordinator node that is required by software-defined networks. Now, how are we trying to solve this issue? With our system ProgDTN, Programmable Disruption-tolerant Networking, we aim to make also disruption-tolerant networking programmable by the operator. That is to say, we enable the operator to modify the routing behavior of the software without having to modify the software itself. We also allow them to make use of context information to make better routing decisions. We will get to a slide later on in this presentation where I will explain what we mean by context information. To maximize ease of use of our system, we decided that the behavior should be defined using a common, popular, general-purpose programming language. With our system, the operator can modify the behavior of the networking software using configuration supplied at startup rather than modifying the software itself. Also, it allows them to use their domain knowledge, that is to say, their specific knowledge about their specific circumstances to define a behavior which is most optimal for them. Now, for the architecture of our system, we built ProgDTN as a component of DTN7. DTN7 is a fully featured DTN networking suite, which we have developed in-house here at the Distributed System Research Group in Marburg. It implements the Bundle Protocol version 7. It is a fully standards-compliant implementation. It is written in pure Go, which is quite nice because Go has a very powerful build chain, which is to say that it can build you a native executable for nearly any hardware or software architecture you can think of. Also, we designed it from the ground up in such a way to make it easy to implement new routing algorithms. However, of course, you still need to know about the internals of DTN7 and you still need to speak the Go programming language to do so. But now what we have done is implement ProgDTN as such a routing module for DTN7. It abstracts away all the internals and the operator can just define the behavior quite easily. Now we will take a little detour into the inner workings of DTN7, or more in general, any software which is compliant with the bundle protocol version 7. In the bottom right, you can see the application agent. This is basically the gateway to the world. It provides an external interface. In our case, you can choose between either REST or WebSockets, with which external tools can insert and retrieve bundles. In the parlance of the bundle protocol, we do not speak of messages, but rather bundles. So anytime I say bundle, you can just think of a message. Once a new bundle has been created, it first gets stored in the local on-disk storage because we are operating in a store carry forward architecture, and so we first need to store it before we can carry and forward it. And then every now and so often the daemon DTND will come around and pick up all the bundles from the local storage and dispatch them by passing them and a list of all currently connected peers to the routing algorithm, which then just needs to return a subset of these connected peers, and then the message will be forwarded to exactly these peers. The actual device-to-device communication is abstracted away using a concept called a convergence layer adapter. This is how the bundle protocol abstracts device-to-device communication. You have a very simple interface, basically just send and receive message, and then the actual minutiae of the communication are abstracted away by this CLA, and it could be really anything. It could be Wi-Fi, it could be a directional radio link, it could be anything you can think of really. The other side receives the bundle via their CLA and then also stores it in their local storage. And if there is a local application agent which has registered the correct recipient address, it also is provided to this application agent, so it can be then queried by external tools or users. As previously mentioned, ProgDTN makes use of context information to improve forwarding decisions. Now, what is context information in our, context? There are two types of context information, node context and bundle context, though that is a bit of an arbitrary distinction because in both cases context information looks very similar. Context information is arbitrary key value data. We make no limitations as to what can be context information. We place no restrictions on the semantics of what can be context information. It is in fact up to the operator to know what kind of context information is important for their scenario, to define the semantics, and then to write a routing script which is aware of these semantics and uses the data in the correct way. In this particular example you see here on the slide, we have two pieces of context information. We first have the speed, which could be provided by something like a GPS module, and then the device's battery level. Context information is provided to the daemon via a REST interface, so you can have an external sensor or something like, as I said, a GPS module, which uses REST to just push new information, new context information into the node every now and so often. The common popular programming language that we have chosen for our project is JavaScript because, as we have been told, it is the world's most popular programming language. And also with JSON, it has a native way of marshalling and unmarshalling complex data, which also works quite well here because, as I said, context information is key value and the key is just a string, and then the value can be arbitrarily complex data marshaled in JSON. So the operator writes their routing script in JavaScript, which gets loaded by the daemon at startup and then gets executed by an embedded JavaScript engine. This embedded JavaScript engine itself is written in pure Go, and thus we maintain the high portability of our Go-based system. What are the concrete steps that context information takes? Where does it come from? How does it aid in making routing decisions? We receive our own context information from external sensors via the embedded REST interface, but we also receive context information of our peers. For this, we have this special message type, the context bundle. Whenever two nodes meet for the first time, they exchange context information using this special message type. And also, if at some later point the context information of a node changes, it will broadcast these changes to all its connected peers. Once a routing decision needs to be made, the embedded JavaScript engine is passed the routing script as well as the node's own context information and all the peers' context information and the bundle itself, which may also have context information attached to it. The embedded JavaScript engine then executes the routing script, which can make use of all these pieces of information in an arbitrary way as defined by the operator to come to the best possible forwarding decision. Lastly, we come to the evaluation of our system. We decided to evaluate ProgDTN using a simplified emergency scenario. You can see it in the figure above my head here. We have a sort of 3-ring model where in the center we have the coordinator node. This is basically a stand-in for something like a local emergency dispatch center. In the middle ring we have a few responder nodes, which are our stand-in for first responders, so something like the fire brigade, civil security, or something like this. And in the outer ring we have the civilians, which is the general populace. Data flows along one of two axes. We can either have broadcasts by the coordinator meant for all the civilians. This simulates informational broadcasts by the authorities to the citizenry, informing them of the situation or maybe making recommendations. Alternatively, we have unicasts by a citizen, by a civilian to the coordinator node, which might be a citizen trying to contact the authorities to inform them of maybe an emergency, of their situation, to ask for help. We implemented this scenario in the Common Open Research Emulator Core, which is a network emulator, which means that we can run actual real-world software, which will run on lightweight virtual machines that communicate with one another. The variables which changed between experiment runs were on one hand the payload size, which could either be 1 kilobyte, which is approximately the size of a text message, or 1 megabyte, which could be a short-ish audio message. Also, we have bundles per node, that is the number of messages that each node sends over the period of the experiment, which was 1 hour each. Lastly, we have the routing algorithm, because we wanted to compare ourselves to some more established algorithms from the literature, and so we have epidemic routing, binary spray and wait, profit, and delay tolerant link state routing, DTLSR. Each experiment was run 5 times, using a pseudo random number generator to vary the time at which each node sent messages. The pseudo random number generator was initialized with fixed seeds to allow for reproducibility. Here on my left you see the actual JavaScript code which we used for our ProgDTN system as part of these experiments. The general gist of it is that information again flows along one of two axes, which means that the coordinator will only send out messages, it will never relay messages. The responders will only relay the coordinator's messages to the civilians and the civilians' messages to the coordinator. And lastly, civilians will relay the coordinator's broadcast among one another, but they will not relay other civilians' messages. This way we ensure there are no unnecessary transmissions and each transmission is always in service of actually delivering the bundle. So what were our results? First and foremost, we looked at delivery ratio. That is to say, how many of the bundles sent actually make it to their intended destination. As you can see here, ProgDTN, which is the light blue bar, works very well for all load scenarios. It works as well as the best other algorithm, and a bunch of other algorithms work significantly worse. Especially note epidemic routing, which starts off very well but then quickly drops as load increases. This is basically because epidemic routing just floods the network with the messages, and so very quickly the network becomes overwhelmed and can no longer deliver these messages. Also, as you can see, profit really never goes beyond 50% delivery ratio for any of these scenarios. Then we have the delivery time. So how long does a bundle which does reach its destination take to do so? You can see all of these algorithms struggle with outliers, but this is to be expected because we are in a delay tolerance scenario, so there will be delays and there will be outliers. As you can see, ProgDTN is at least on par, if not better, than basically any other algorithm for this scenario. Next, we have the total number of transmissions. Please note the logarithmic y-axis. As you can see, epidemic routing produces about 100 times the number of transmissions than ProgDTN, but as you saw on the previous slide, this does not translate into a higher delivery ratio. Rather, it just overloads the network and it basically makes everything worse. For the other algorithms, we can see that ProgDTN does not produce a significantly higher number of transmissions than even the best other protocol. Next, we have the bundle overhead. As I previously mentioned, ProgDTN occasionally sends messages to peers, which include the context information of this node. Of course, these bundles do not directly contribute to the delivery of messages, and thus they are considered overhead. The other two protocols which use some sort of metadata message are Prophet and DTLSR, but epidemic routing and binary spray do not use any sort of metadata messaging, so they are not present in this graph. As you can see, all of the algorithms start at nearly 100% overhead. This is because at the beginning of the scenario, all the nodes already exchange metadata messages, but there are no real messages on the network yet, so we have basically 100% overhead. But for both Prophet and ProgDTN, this overhead drops exponentially as time progresses, while for DTLSR it is more or less linear. Lastly, we have the computational overhead. On one hand, we have the routing decision time, that is to say, how long does it take to make a single routing decisions. Here we also have ProgDTN epidemic and ProgDTN binary spray, which are basically re-implementations of epidemic routing and binary spray and wait using our ProgDTN system. And as you can see, if you try to just emulate another routing algorithm in JavaScript, as you can expect, it takes a lot longer because you have to fire up the embedded JavaScript VM every time you make a decision. And of course, this will take longer. But as you can see, ProgDTN emergency, which is an algorithm specifically designed for this scenario, fares a lot better. On the bottom, we have the CPU utilization of 3 different routing algorithms. Again, we have epidemic routing, ProgDTN epidemic, which is epidemic routing in ProgDTN, and our specialized ProgDTN emergency. And as you can see, the re-implementation of epidemic routing in ProgDTN results in a lot higher CPU utilization, but ProgDTN emergency has a lot lower CPU utilization, which again is because we are more conservative with our network utilization. We send fewer bundles, thus we need to make fewer forwarding decisions, and thus there is in general less load on each of the systems, and so we have less resource utilization. In general, we see that ProgDTN emergency performs on par, if not better, than any other algorithm for this scenario. Of course, this does not mean that the other routing algorithms are bad. It just means that if you are smart, if you define an algorithm which is specifically designed for your scenario, you can outperform these more general purpose algorithms. And this is it. I thank you for your time. In the bottom left, you can see the link to all our sources and artifact. The entire system is open source and can be reviewed. We also make all our experiment data available freely on the internet. If you have any further questions, feel free to contact me or one of my colleagues at our email, and we will be happy to answer any questions. Thank you very much and have a nice day.